Hello, good morning everyone. Today I will continue with you on the topic that we spoke about in the previous session. I will continue on eigenvalues and eigenvector. This is really a very important topic and with a lot of applications almost in every field of STM. So today I will continue on this topic of eigenvalues and eigenvectors. I need to continue with you, if you remember, in the last session we already did go through how to get the eigenvalues and the eigenvectors from doing exactly the characteristic equation, if you remember. Then after that we solve the system. I want you to review these steps with me by solving this problem, trying to get the eigenvalues and the corresponding eigenvector for this problem. For example, let's say that I have C here, and C is the matrix 3 by 3, which is a square matrix. For the first row, it's 2, 1, and 0. For the second row, it is 0, 2, and 1. For the last one, it's a couple of zeros, then 1. If I want to evaluate the eigenvalues corresponds to this problem, all I have to do is to use the characteristic equation, which states that A minus lambda I equal to 0. So forming this equation will help us out in order to get the various values of the eigenvalues. So all I have to do once more is to get those determinant parentheses. Then I will start with the principal diagonal, 2 minus I, 1 and 0. For the second one, it's gonna be 2 minus lambda, then 1. For the last row, it's gonna be 0, 0, 1 minus lambda, and I will put all of this equal to 0. Then I will go to the second step of trying to expand this determinant easily, which is gonna be, I will use Sar's rule of course, and you can use whatever you want. But the simplest in this way is to use the method that I told you about. It's about Sar's rule. So I will start with multiplying the elements of the principal diagonal, and this will lead to have 2 minus lambda times 2 minus lambda times 1 minus lambda. This is for the principal diagonal. Then I will multiply the two elements of the lower base times the first, which is going to be 0. Also, the other way around is going to be 0. For the remaining, it's going to be zeros. All of this had to be put equal to 0 in order to get your eigenvalues. So now I'm having 2 minus lambda to the power of 2 times 1 minus lambda equal to 0. And this will mean that we have two values for lambda. The first of them, the first one is lambda equal to positive 1, let's say, and the second is lambda equal to 2, but take care, it is repeated 2 times. So now for this value and for that one, this one which for lambda equal to 1, we have just only one on algebraic multiplicity as we defined in the previous session. Okay, and this will have an algebraic multiplicity of 2 because it is repeated 2 times. These are the eigenvalues corresponding to this matrix. So simply, if I want to get the eigenvalues corresponding to this problem and also try to get the eigenvectors corresponds to this problem, this is the first step that we will have to do. For the second step, I will use this huge advantage and I will start by the following 2 steps. The first step that I'm using now is to get the first vector, which is u1, and it is corresponds to lambda 1 equal positive 1. Then I will go for u2, the second vector, which corresponds for lambda 2 equal 2. All I have to do now is just trying to make things very easy. So I'm going to use the system or the homogeneous system of A minus lambda I, okay, times the X or the time U, let's say U to keep all the symbols together, which will equal to 0. In order to solve this system, it means all I have to do, take the elements of this determinant once more. So they will be 2 minus lambda, which is 1. Then you have 1 and 0. And this is the general form of the system or the augmented matrix generated by this homogeneous system of equations. For the second row, it's going to be 0, 2 minus 1, 1, then 0. For the last one, it's going to be double zeros, then 1 minus 1 equal to 0. And this will lead to having this matrix, which is simply can be put on this form if you are following me. 2 minus 1 is going to be positive 1. Then I will have positive 1, 0, and 0. For the second row, it will start with a 0, 2 minus 1, which is positive 1. Then I will have another 1, then positive. For the last row, you will have a complete row of zeros. Now, I can get easily to the reduced echelon form simply by multiplying the second row by negative 1 and adding it on the first row to get to the nearest form of a reduced echelon form. And this will leave us with a form like this, with a rank of 2. These are the last row. The second row will be a 0, then I will have 1, and then 1 equal to 0. Multiplying this by negative and adding on the first row will leave us with 1, then 0, then negative 1, and it's equal to 0. Now I'm ready to expand this and to get to a form of this vector. The vector that I will have is for, if I used x, y, and z for the components of the first eigenvector, it's going to be really very simple. I used on using the first component, second component, third component, which will make no difference. So I will start saying that this is u11, this is u12, and this is u13. So I'm getting the first eigenvector corresponds to the first eigenvalue, which is 1, and it contains 3 components. So simply, for the first row, I will have this relation that u1 sub 1 minus u13 equal to 0. And for the second row, exactly the same, it will state that u1 second component plus u1 over 3 equal to 0, and this will lead to that you have a relation connecting these components all together. So this is the first component, which equal to u13, or simply x equal to z. And for the second row, you will have first vector second component equal to the third component, as you can see, but remark, there is here a negative sign. Now, I can say that u1, the first eigenvector, consists of 3 components, u11, u12, and u13. I will use these relations and I will get them u13 minus u13, either take u13 or this component as a common from all of them, then you will have the eigenspace of this eigenvector, which is simply could be done by considering u1 over 3 equal to 1 or equal to 2 or whatever. So you will end up having this eigenvector. I hope you can see it. It is 1, negative 1, then positive 1. So this is for the first eigenvector. All these steps will be repeated once more, but it will be repeated relative to lambda 2 equal 2. So once more, I'm recalling all of these steps once more. So I will have the system, the augmented system of equations, which is simply can be given by 2 minus 2, which is gonna be a 0. Then I have 1 and 0 equals 0. For the second row, it's gonna be a 0, 2 minus 2, so it's gonna also be equal to 0. Then I will have 1 equal to 0. For the last row, I would have 0, 0, then 1 minus 2, which is negative 1 equal to 0. Exactly like what I did in here, I will try to get as close as it possible to reduce the echelon form, which is really very simple. I can remark that if I added the second row on the third one, I will be ending up this debate by having a 0, 0, 0, and 0. For the second row, it's gonna be 0, 0, 1, and 0. For the first one, it's gonna be 0, 1, 0, and 0. This form implies that I'm seeking now the second eigenvector first component, the second component, the second vector third component. So once you try to get the values of all of this, you will end up having the second vector, second component will equal to a 0. The second vector, eigenvector, with respect to the third component equal to 0. So once more, if I'm considering U2 as 3 components, x, y, and z, or U2 first component, U2 second component, U2 third component, and start to substitute with all of these values, I will have a 0. I'm sorry for this. I will have first component, it will remain the same. For the second component of this second vector, it's equal to 0, and the same for the third one. So, which simply, if I consider U21 equal to positive 1, I will have the eigenspace, or the basis for this eigenspace corresponds to 2, which is 1 and double zeros. These are the 2 eigenvectors corresponds to these 2 eigenvalues. We got them carefully from solving this problem. So once more, now I have the following in a summary. For lambda 1 equal to positive 1, the corresponding eigenvector that you will have is simply 1, negative 1, and 1. And for the geometric multiplicity of this eigenspace, it contains just only one vector, so it's a 1. For the second, which is simply 1 double 0, okay, this is for lambda 2, which is just only 2, and the corresponding eigenvector is given by 1 and double zeros, and this eigenvector is of geometric multiplicity also equal to 1, because just only one vector forming a basis for this eigenspace that I told you about. So once more, here we go. I'm taking the principal diagonal, subtracting lambda from it, trying to expand this equation. You will have this form. Once more, here we have 2. The algebraic multiplicity is 2 because the power of this number is 2. Okay, I'm trying to work with lambda equal to 1, exactly similar to what we did. This is the augmented matrix. This is the system that we are trying to solve. You will end up having these values. Okay, x equal negative y and y equal negative y. I believe there is just only a typo here in this problem. And you will end up having, this is the vector that we are talking about, which is negative 1, 1, and negative 1, similar to that vector exactly. If you look closely to the value of this vector and to the value of that vector, you will find if we multiply this by negative 1, you will have this form exactly, which is similar to each other. Okay? In a similar manner, I can do this for lambda equal 2, in a similar manner, I will continue with all the steps that we have reached, that y and z equal to zeros, and by the end, we will have 1, 0, as an eigenvector, exactly like what we did in our solution for this system, or for getting the eigenvalues of the system. The comments are really important, and you already have this on your slides. I've tried to download all of them and sent to you all of this. So note in the eigenvectors -1, 1, -1, or 1, -1 and 1, 1, 0, they are linearly independent vectors, and we can get a basis for R3 from DC. Remark that the characteristic polynomial a minus lambda I may have complex roots for another problem. I'm talking for another problem. Once you try to get your characteristic equation, maybe for some cases of these matrices, you may have complex roots as eigenvectors, as eigenvalues, and of course you may have the corresponding eigenvectors also in a complex. Remark the algebraic multiplicity of a root, the algebraic multiplicity of this equation, or the characteristic equation, it is simply the power or the number of repetition of the lambdas that you can find. Here, solving this fundamental polynomial, you can use all the theories that you want in order to get these roots. This is stated here. Note that by the fundamental theory of algebra, a degree n polynomial has n roots counting multiplicity and real and complex roots. Okay, stating also for the same, if we are talking about the eigenvalues. Now it's about the eigenvalue of an n by n, the set of eigenvectors associated with this eigenvalue. It's going to be the set of vectors, and this is exactly what we did. This is the set of vectors on this basis, or this is this set of vectors. This is the base of this set of vectors corresponding to the eigenvalue that we are using. It's stated in here. Also, the algebraic multiplicity is defined. The geometric, yes, this is the geometric multiplicity. Let lambda be an eigenvalue of n by n matrix, dimension of the eigenspace of lambda. So I'm coming to the eigenspace of lambda of the eigenvector corresponds to lambda equal 1, and you have one vector generating this eigenspace. So the geometric multiplicity will be one vector. In here you have also one vector, so the geometric multiplicity is also 1. It's stated here in this definition that eigenvalue of an n by n matrix, the dimension of the eigenspace of lambda, dim E, is called the geometric multiplicity of lambda. This is what we mean about the geometric. So, once more, short couple of lines. If you are seeking getting the algebraic multiplicity, it's really very easy to have. It's just the power or the number of repetition of your eigenvalues. For the geometric multiplicity, it's the dimension of the eigenspaces relative to your eigenvalues. So you get your eigenvector corresponds to a certain value of lambda, then you define or count the number of vectors over there. This is the dimension that I'm telling you about a geometric multiplicity. Let A be an n by n square matrix. Let lambda be and its eigenvalues, counting multiplicities and complex numbers. Then we will have the following. These two remarks are important. You may need them down the road. You may be asked about them in exams. They will make your life easier, but you will have to keep them with you just in case if you need to use them at any time. The first of them states that the determinant of A is equal to the multiplication of the values of your eigenvalues. So if I have, for example, this matrix, if I get the determinant of this matrix, which is going to be simply equal to 4, 2 times 2 times 1 by first rule, it's going to be 4, then the remaining parts will equal to 0, so the determinant of C is equal to 4. And it's exactly like multiplying 2 by its multiplicity, so 2 to the power of 2, which is 4, times 1, they are similar to each other. Another remarkable remark, another unmissed remark, which is the trace of a matrix. It's equal to the sum of the eigenvalues. So if you add the elements of the principal diagonal, which is simply 2 plus 2 plus 1, which is going to come up to 5, it's going to be exactly the same like adding the values of your eigenvalues. So it's a 2 plus 2 plus 1. So also it's 5. So more than perfect. So it is as I told you, the trace of a matrix, which is the sum of the principal diagonal elements, and it will equal to the value of lambda. Also, if you need to have the determinant of A, it's going to equal to the multiplication of these eigenvalues exactly. Okay, last theorem states that for a distinct eigenvalues of A, you will have linearly independent vectors. This is really very important. So once you try to solve your, try to get your eigenvalue eigenvector, and you have different or distinct values of values, you will have linearly independent set of vectors stand for the eigenvectors corresponding to them. Okay, now I want to introduce the similarity of matrices. This part, it has theories, it's already written with you. I will try to go through it a little bit faster because I need to show you also two problems, or one of the major problems in this part. So, what we are trying to say is that simply, I can have two matrices similar to each other. This is gonna have a huge advantages and impacts down the road on the properties that we can take advantage of. So now, if I have A and it is similar to B, okay, it will have to, these two matrices will have to satisfy this relation. So, reading this definition, A and B and square matrices, we say that A and B are similar matrices if there exists an invertible matrix S. So, if I have an invertible matrix S, such that B will equal to S minus 1 times A times S. Now, I will try to get this matrix. If you remember the previous session, once we started on evaluating the eigenvalues and eigenvectors, I did the eigenvalue and eigenvectors, getting the eigenvectors, if you remember from the previous session, normalized them, I will talk about this later on, then getting a matrix from the eigenvectors, considering these eigenvectors as a column of this matrix. This matrix is the S matrix that we are talking about. I've tried to just to be a little ahead of the theories in order to tell you, to be able to convey the message for you. Also, if you have two matrices similar to each other, remark that the following, that these two matrices have the same or the corresponding values of eigenvalues. So, if I have two matrices and they are similar to each other, their corresponding eigenvalues will be the same, or the eigenvalues will be the same. Now I will talk in specific about a linear transform from E to E. So it's stated here, this theorem says that similar matrices have the same eigenvalues, blah. However, their eigenvectors are in general different, and you saw that it's possible. Let's now go back to linear maps from n dimension, and we will introduce the matrix. All of this are introduction on how to get the U matrix, or the matrix that's responsible about getting a similarity. Not just only this, but also the diagonalization that we will see. Now, here the system that we can use, if you remark, it's the linear transformation T of U, which equal to lambda times U. Okay, so from a point of view of a linear mapping, and once you are doing an identity, or you are transforming from E into E, you will have your coordinate sequence matrix, and we really did go through this in linear transform. This matrix can be put in this form, which is A minus 1 times, or S minus 1 times A times the S matrix. This is what's actually stated in the previous, but in terms of a linear transform. So this is mainly what we are searching for. We can diagonalize some classes of matrices, And this classification or diagonalization will exist if you have your system or the eigenvalues having and the corresponding eigenvectors having equal algebraic multiplicity and geometric multiplicity. Then you will be able to get this diagonalizable form. If you remark, stop at here. If you remark, in the previous session, we already did all of this at once. So we started with a symmetric matrix. This symmetric matrix helped us to get the eigenvalues, corresponding eigenvalues. For each one of them, we got a corresponding eigenvector. Using these eigenvectors, we succeeded in finding the S matrix, which can be used in diagonalization just simply by making this multiplication. Okay, once more, this is what's stated here. One of the greatest advantages of using a diagonizable matrices and taking advantage of the similarity is simply, if I have a to the power of n, it's not going to be easy to deal with. But if you have a similar matrix to A, which is a diagonizable matrix, so actually a to the power of n will be similar to d power n if you succeed in putting it in this diagonalization form, and the elements of the diagonal matrix will be simply the eigenvalues. This is what's stated here in these theories in details. You will find them on your PDFs that I sent you earlier. So now I will have to solve another problem going through all of these steps with you. Okay, perfect. Also, it's stated here that n square matrix is diagonizable if and only f A has n linearly independent eigenvectors, and this will happen when you have different eigenvalues. That's there exists a basis Rn considering the eigenvectors of A. Not that since we consider a real matrix, of course, if we have real matrix, you will have real values of eigenvalues. The equation of how to diagonalize n by n, we will see it, okay? So now we have in resume D, as I told you, by the end of the line, D equal S minus 1A by S, and the S matrix is the matrix with columns equal to the eigenvectors. I will show and review this with you for this matrix. But before going to solve this matrix, I want to introduce also, I want to go just a step ahead and give you what's a quadratic form, or from where we can get this symmetric matrix. It's really a piece of cake, and it's really very simple. Quadratic forms could be on this form. Listen to me, please. If I'm in 2D, if I'm in R2, a quadratic form could be A of x squared plus, let's say, 2p x and y plus c y squared plus some d times x plus some e times y plus some f equal to 0. This is what's called a quadratic form, or a general quadratic form in R2. If you take a good look for this quadratic equation in R2, it could be an equation of a circle, or an equation of an ellipse, or an equation of a hyperbola, or an equation of a parabola, and so on. It could be a lot of things. If I want to have it on the normal form and know that the exact form, I can use advantage of the formulation of the quadratic forms and the relation of the matrix that we can use in order to get a diagonizable matrix, as we will see down on those slides. But this is as a summary, and I will need it also in this presentation or in this form. So simply, if I have something like this, I can get my symmetric matrix, which I can analyze and get its eigenvalues and eigenvectors and do all the blah 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 steps that we talk about. How to get this quadratic matrix? All I have to do is to consider the axes, which is x and y. So this is x and y, those actually the main axes or the frame of reference in R2. and I will put a matrix which is 2 by 2 in here. I will show you how to extract it from this form, times an xy, okay, in a similar manner like this one. So you will have S transpose times A times S transpose. So for this matrix, the elements of the principal diagonal are simply the elements that stand in front of x squared and y squared. So I will have A here and C over there. Then for the term xy, I will take its coefficient and then divide it by 2, putting half of it here in the element 1, 2, and the other half is here. So this is the matrix that we are talking about. Okay, let's reverse that thing here in this problem. He's giving you the A matrix and he's telling you, or he wants you to write a quadratic suitable form relative to this matrix. How to do it? I will reverse the whole issue. So I will say that this is the x and y, because it is in 2D, and that's the transpose of this matrix, which is x and y. The matrix that I'm targeting is in here, which is simply having -1, +1 for the elements. It's a symmetric matrix. So the corresponding quadratic form for this matrix could be this number in front of x squared, so it's going to be -x squared. And then that number, it's in front of y squared. I will take one of these numbers, okay, the numbers on the sides, or 1, 2, because it's a symmetric matrix. I will take this number multiplied by 2, so it's going to be plus 2 of an x plus y. Then any number of x, let's say b of x, plus a c of a y, plus a d equal to 0. This is the general quadratic form. So, if I give you this matrix, if I give you this quadratic form, you should be able to get this matrix out of that form, which is simply a piece of cake. All I have to do is to take the coefficient of x squared, put in the element 1, 1, taking the coefficients of y squared, put in the element 2 and 2, taking the number which is x times y, divided by +2, putting half of it on the element 1, 2, and the other half on the element 2, 1. Now you have your quadratic form. So the answer for this question is simply -x squared 2xy minus y squared, blah, blah, blah. Now I have the quadratic form. I thought to introduce this issue now for you, just to know from where we got this matrix. And we will go through it down the road by the end of this lecture, hopefully. Now, once more on the double, I need to find everything. I need to get the eigenvalues of this matrix, the corresponding eigenvectors, to check the probability since it is a square matrix. So, and it is also symmetric one. So I will have orthogonal matrix, which is the S matrix responsible about the diagonalization. I will show you how it is orthogonal. We already did do that previously, but I will review it with you. And also how to take advantage from the normalize the model matrices, which having a great advantage, their transpose is their inverse. So I will start all of this by taking this matrix, which is really a very simple matrix, -1, okay, +1, 1, -1. This is the matrix that we are talking about. -1, 1, and -1. Then I will try to subtract or to get the characteristic equation, which is simply A minus lambda I from the same dimension and equal to 0. If we did so, we will have to solve this equation, which is simply -1 minus lambda. Then I will have 1, 1, -1 minus lambda, and put all this equation equal to 0. Once you do so, you will have 1 plus lambda to the power of 2 minus 1 equal to 0, which is gonna result to having lambda squared plus first second times 2, which is gonna be 2 over lambda, plus 1 minus 1 equal to 0. These two elements will be cancelled together easily. So now I will have this form, which is simply lambda times lambda plus 2 equal to 0. This is the matrix, or I'm sorry, this is the equation that we will try to solve. So I'm having lambda 1, which equal to 0. This is the first eigenvalue. And the corresponding eigenvalue for this is going to be lambda equal to negative 2. Corresponding to each one of these eigenvalues, I can get simply the corresponding eigenvector. So I will start with getting u1, which corresponds to lambda 1 equal to 0. And this is really a piece of cake. All I have to do is to once more solve the homogeneous system a minus lambda I times x equal to 0. Try to solve this homogeneous system, which is simply gonna be, which is gonna be minus 1, 1, 1, negative 1, of course minus 0, okay, I will write it for you now, minus 0, and this is because the first eigenvalue is 0. Try to solve this system. So the second step, it's gonna be having a negative 1, positive 1, 0, then I will have 1, negative 1, and 0. And from this, I would have the following, okay, remark. So it's gonna be 1, negative 1, and 0, and all the remaining elements will be zeros. Now you have u1 first component, u1 second component, or x and y. And this is will result to u11 minus u12 equals 0, which means the first eigenvector with first component equal to first eigenvector